OK. Et aujourd'hui, on a Mariana Penna Lima, un membre de groupe depuis 1 an et demi maintenant, 2 ans?
Non, un an et 3 mois.
1 an et 1 quart, qui va parler de, comme vous voyez, le Numerical Cosmology Library. On a aussi Sandro qui travaille avec elle sur le NumCosmo et je viens de voir que Cyril Du est aussi sur la liste d'auteurs. Alors, c'est vraiment un truc de l'APC maintenant. Allez.
Bonjour à tous. Je vais présenter en anglais. Donc,
Very
good
good.
morning. I'm going to talk about the Numerical Cosmology Library, which we have been developed for, I don't know, 8 years. You started, and Cyril, for example, is working with us 1 year now. So
I saw you give a presentation about it in Búzios, in Brazil, a couple of years ago.
Yeah. But a lot of modifications there. So here today I want to give you an idea of the framework, NumCosmo framework, and also advertise it because we think it's a good framework for the astronomical, astrophysical, and cosmology community to work together in a collaborative way. So NumCosmo is a free software, C library. We use a GPL license, and the main goals are to test the cosmological models using observational data. And here, test cosmological and also astrophysical, it will be clear later, and provide a set of tools to perform cosmological, astrophysical calculations. Also combine these multiple probes and perform data analysis. The NumCosmo is written using the framework of GObject, which allows object-oriented programming in C. It also provides an easy way to deal with memory allocation, things like this, garbage collection, okay? And we also use the GObject introspection, which provides automatic bindings between C, Python, Perl, Java, and other languages. Sandra also implemented the serialization feature, and yeah.
So this runs from C or from Python?
Yeah. And for example, in order to get also optimize the codes, we have been developed everything in C, but the scripts, for example, to run MCMC analysis and things like this, we make scripts in Python such that we can also connect directly to make plots, and it's easier.
Okay. That was my question. Yeah, that's good.
But today, currently the latest version, you can also create an object written in Python or Perl, for example. You don't need to read it in C. So we think that way we are going to be able to reach more people, more collaborators. Here I introduce basic concepts. The library is built on the top of this NCM, NC, NCM model, NCM MSET, NCM data, and dataset. So NCM, this prefix, we use it for all objects which are not related with cosmology or astrophysics. So here it stands for NumCosmo Math. And an example of this object is the object related with the bidimensional spline interpolation, for example. We also have matrix, vectors, objects, okay? And also the statistical tools are written under NCM. And the prefix NC we use to represent the codes related to cosmology and astrophysics. So NCM model is a G-object, an abstract class, which basically defines a set of parameters. So I will show two examples where we can find, for example, one model of our library are the homogeneous and isotropic cosmological model. We also have a cluster mass. And so,
why do you need the NC without the M? I mean, if I write my own code and I call this library, do I have to name it NC, or you just use that as a convention?
You don't need to name it, but for the automatic bindings be generated, it has to know where to go, where each object goes. So you put the prefix inside of the code, so you can generate the bindings.
Okay.
It's just a naming convention that they use to parse the code and find what is going where.
I didn't mention before, but this G-object framework and G-introspection, you have a fixed way to document your functions, all your objects. And given these, the bindings can be G-object introspection can act and generate the
I've never used it.
bindings.
Okay.
There's a lot of translation between C and Python, for example, so you have to give some hints for the bindings to be generated automatically.
So this introspection, it means that it basically reads the code that you...
Exactly.
And it knows how
It
to...
parses your
How to
code.
deal and connect them. Yeah.
It parses your code and generates like an abstract interface, and then on top of this abstract interface, people build some interface with specific language like Python, Perl, and for this main language, this interface is already ready. So you don't just need to write in the right way, so you have the bindings.
And everything that doesn't follow this convention is ignored, basically?
You can ignore. You can also just set. I don't want these to be binded.
MSET is a collection of models which can contain models of the same or different families. So, for example, this is necessary to perform a combined probe analysis. So, if I want to fit a cosmological model, cluster redshift distribution, cluster mass distribution, so each one it will be defined as a model. And then I combine it, when I call it to perform my statistical analysis, these three objects will be passed and compose this model set. Okay. So this is more for the theoretical part, let's say. And then I have the object related to the data, to the observations. So we have these NCM data. Is an abstract class which encapsulates functions such as the resample functions, -2 logarithm of the likelihood, bootstrap resample, and many other functions. Okay, so here we have the abstract definition, and then when you implement data, let's say BAO data, you have to provide your not necessarily have to provide all these functions, but it's where you are going to implement, for example, -2 logarithm of the likelihood. And things
So
like
this is, for the CMB, this would be the power spectrum and the class that reads and finds chi-squareds and things like that.
Exactly.
Yeah. Yeah.
And then a data set would be the CMB power spectrum and the lensing spectrum.
And the lensing spectrum and supernova data and cluster data and things like this. Okay, so data set is a collection of the NCM data. So here I have a first simple example. If we use supernova data, for example, I can write the likelihood logarithm of the likelihood function like this. It follows a Gaussian distribution. Where here I have a covariance matrix Here, specifically, this is an object where the covariance matrix is not diagonal. Okay. So in this case, we have, if I want to fit cosmological model and the parameters, the cosmological models, which are inside here, the luminosity distance, and also if I want to fit the astrophysical parameters, where alpha and beta are related to the stretch, luminosity and color luminosity, and M1 and M2 are the absolute magnitudes. If I want to fit both of these models using a MCMC, I will define an object called MCM fit, and then one child of this abstract class is MCM fit MCMC, for example. We have Monte Carlo, I'll show some examples. So we have different childs of this abstract object, MCM fit, and then this object will be fed by an MCM M set. This is our model set. With here, it will be composed by high Cosmo object. High is a homogeneous isotropic cosmological model. Specifically, we have a child of this object, which is dark energy XCDM, which is the dark energy with W0 equal to a constant. Okay, we have also the child lambda CDM. We have the W0, W1 parameterization. So here you can find different cosmological models. If you have a proposition of a new cosmological model, given an isotropic and homogeneous metric background, you will implement it as a child of NC high Cosmo, which is an NCM model. So here the cosmological parameters like omega m, omega b, H0 will be these parameters will be defined here. Okay.
Do you have a minuit as a filter, for example? Do you have minuit as a filter, for example?
I will mention this later. We have NumCosmo has we use NLOPT, GSL algorithms, and there is another library, Lima is also. So we have, I think, more than 70 algorithms to compute best fit to minimize. So you can test what is the best one for the most suitable one for your problem. And as we link with these external libraries, we have available more than 70 algorithms to minimize, for example, to find the best fit. Okay? And in particular, for supernova, in this case, where the covariance matrix is not diagonal, the object related with this data, with this model, is NC supernova Distikov. Okay, it's the name we gave, and it's also an NCM model. Why? Because I have these parameters, astrophysical parameters, that I also want to, maybe I want to fit.
But that's my question then. So those are, I would call those experimental parameters or something.
Mm-hmm.
They don't, and those come in. Do you have to write code that mixes the cosmology and the experiment? Is my question.
The idea is that you don't need to write any code mixing these parameters.
Okay,
I mean, just write each model, and the MCM set take care of mixing and combining and using them together.
Okay, but how does it come up with, I mean, there could be covariance, well, I guess, alpha and beta would not be covariant with H naught, I guess, or something.
Oh.
Right? I'm just worried about, some of the really special cases where you have to go through and you have to try and understand is, for example, theta MC in CMB, the size of the spots, and your beam width.
Mm-hmm.
are going to be really hard to separate, and there's going to be some covariance in there.
But,
So you have to write a code that somehow tells you that.
your model.
If you give it, but if you give it the CLs and the covariance matrix of the CLs, it's going, in your model you will have the beam size and
Exactly.
data and things like this. So it will come out from the fit.
So it will just come out as part of the MCMC. It
Yeah,
should come out.
exactly. So they will be parameters, experimental parameters of your
Yeah, it's
object.
MCMC saves you.
One of the
It will lead
outputs will
with
be
everything together. Yeah.
the full covariance matrix
Yeah,
between
exactly.
the whole set of parameters.
So when you give it, suppose you going back to, so you give it the CLs and the covariance matrix of the CLs, you have to write code that translates the cosmological parameters in your model,
Yes, that's right.
some nuisance parameters, to convert that into a prediction for the data, right? That you will compare, that you will put in the delta M.
Exactly. Exactly.
We have some examples specific how to do that. So I think it's better. In
So-
that case, everything is calculated in the NEC distance. It's just a general model to calculate the cosmological distance. So it gets the cosmology, and from the cosmology it calculates the distance, and then you feed both models with that results. But we have some more complex examples.
So that delta M is calculated in MC distance.
No, the
The
delta M, yeah.
The model distance model is yes.
Actually,
And also
it's
the
calculated by the
luminosity
NEC
distance.
data curve, the supernova distance curve. It gets the results from distance to build the delta M.
They are related.
Okay.
So
I'll wait.
So NC distance is enactment of this model, supernova model, and distance also depends on the cosmological model. Okay, so here this is the beauty, I think, of the library. Everything is written in modules. So
Modules.
So you cannot, you don't need, for example, here inside, I don't need to, it doesn't matter which cosmological model I am using to define this luminosity distance. This equation for looking at the supernova, it will not change if I'm assuming a lambda CDM or any other dark energy model, okay? So this is why we separate everything. So this, which cosmological model will be defined here, and NC distance will look at it, okay? But this guy here does not necessarily need to see in a direct way, okay? I don't know if it's clear.
Sure, and somehow it seems that maybe NC distance should be higher up on the hierarchy.
But
I think that might be by work.
Here,
Well, is it back?
because
Is it
here,
up, going up? Is the flow going up or down?
here, for example,
The flow is down, actually. I think she wrote like who feeds who.
yeah,
Yes.
yeah,
NEC distance feeds, actually is fed by the NEC high Cosmo and feeds the
supernova.
the distance curve.
yeah. Here,
The arrow is wrong. The
yeah,
arrow should be
exactly.
downward.
Oh, okay.
The arrow here.
The
Yes.
distance is like the NC distance is like the -2 log likelihood of everything together.
Actually,
NC distance.
no.
Oh,
No, it's
sorry.
the cosmology, it's the luminosity.
Oh, I'm sorry.
Yeah.
Yeah, that was confusing me too. I think that we're
What? Sorry.
we were thinking NC distance was sort of a chi-squared or something like that.
No.
Right? Yeah.
No. This
It's
object
just
defines
calculates the
the
distance.
cosmological distance.
It's a cosmo. That's the answer.
Yeah, just the cosmological distance. I defined it in this object.
Okay.
Okay. No fit
Yeah. Maybe we should go to the
nothing
examples.
Yeah.
related with this. Okay. And so this is the part related with the models. and consequently with the model set. And here, the other argument that I use to fit the fit object is NCM likelihood. And NCM likelihood will receive as an argument the data set, which in our case, we have here the supernova data, which is the way we assume the distribution for the supernova with this covariance matrix is a child of this abstract, this general class of data, which we call Gauss covariance. Okay, so for example, you can have different observables related with number counts. It will follow a Poisson distribution. So you can create NCM data Poisson. It is generic. It does not. It will not depend on a specific observable. You can use it for clusters, galaxies, quasars. If you are building a likelihood with some number counts, it will follow a Poisson distribution. So these galaxies, clusters, quasars will be some of these NCM data Poisson. As in this case, we have the supernova covariance as a child of this Gaussian covariance data. Okay.
I think the example you should continue.
Okay.
Become more clear.
Okay. So now I will talk specifically of cluster number counts, which has much more complicated structure related with the theoretical parts, for example. So here I define it, and I will try to. Last week we had the Euclid cluster meeting here, and I will try to identify some issues that we discussed in the meeting. So, for example, part of the group building a likelihood assuming a Poisson distribution for cluster number counts. And here we have, for example, this ambiguous implementation where we have this Poissonian term for the total number of clusters, and where n is the theoretical number of clusters that we expect to observe, and this small n is the number of clusters that I observed. Okay, so and here I have this distribution for each cluster where the input is the observable, which we can call here richness of each cluster, and here the redshift. So this will define my likelihood, which will be written, implemented in the NC data cluster and count. Okay. And here I have the which will be related with my model, which is NC cluster abundance. So this function here, I read like this, with this triple integral. So if I can have here more than one observable for mass, for example, we can have Planck masses and lengthy masses as we are working on a project. And then you are going to have another integration over the second mass observable. Okay, so you build this term like this, where here we have the true distribution of halos clusters, and inside this function I have the covariance distance, which we saw that will be related, computed inside this object, NC distance, and this guy here defined as the NC mass function. All functions related with the probability distribution of between the true mass and the observable for my cluster mass will be defined at NC cluster mass, and analogously for the redshift distribution. Okay, So each guy here is a different object that I will build to define my cluster abundance. Specifically, the mass function.
Just to be clear about, I think that the previous slide, you see that the data here needs all these integrals, all these observables to be calculated. So in that sense, it's like the other case, you have the distance that will be fed to an integral that will have the result, and then the data object will put everything together to calculate the -2 log of the likelihood. So it's always in that direction. You have some objects that calculates the theoretical values of the cosmology things, and then that is combined by the data object in the form of the likelihood.
Yeah.
And then the likelihood is the data set and go on.
Yeah.
And why did you have to separate those? Why not?
The data and the
Well,
model?
all of these
Why the
parts,
separation?
yeah.
Because in this point here, you can use different
So
implementations
just
of
to
mass
tweak the
function.
models.
Exactly.
Okay.
So you have to find what is independent of what, and make different implementations of it. Make an abstract implementation, and then you make specific implementations.
So you're really turning cosmology into an object-oriented program.
Yeah,
Exactly.
exactly. This is the idea.
So, for example, here I have to care about the halo dark matter or having n-body simulations with taking into account baryons. We have the true distribution of clusters, and which is not related at this point with the cluster mass. So here I define this object in a general form, and it doesn't matter which multiplicity function I'm using here, okay, or which observable mass probability distribution I will define. This is it. At this point, this is transparent, okay. So, for example, this guy here, the halo mass function, it's written like this, where f is the multiplicity function, is another object, and this term is related with the matter variance object. Okay. So, for example, here are the different multiplicity functions that we implement. Okay. Jenkins, Tinker given the critical mass density or with the mass defined with respect with the mean density, okay, and many others. So when you perform your calculations, you can switch, or if tomorrow someone appears with an n-body simulation or has a way to provide, okay, I have a best or I have a suitable multiplicity function to work in the for Euclid, for example. We will here implement as a child, but I didn't need to change anything above this. Data cluster and count, cluster abundance, it will ignore what I'm doing here. So this is easier to manipulate and control the...
But the difficulty is that you need to know where you go to make this. Right?
Yeah.
So,
where you break things.
Yeah, so you've got... It is nice, you don't have to change anything, but there's got to be hundreds of these low-level routines that you have to know where things are, and does the framework help you with that? How I mean...
Yeah,
okay.
Because you define these objects, and I don't know if I'm used to it, but I think it's simple to manipulate it. And another great thing is that when you perform a new implementation, you can test it independently, and you can assure the quality.
In my experience, you start by writing just a full-blown object with everything together. And then you start to realize that, oh, that part here is independent, so you break it. And then you go in piece by piece just to get a good...
Yeah, but the hard part here is knowing what you two have actually done so that you know what part to break, right?
Yeah.
If it's just us, we can do all of this, but if it's trying to read your minds, it gets harder.
No, but you can't find in the documentation. You have
Okay.
just a tree putting all this.
Do you have a slide with an example of what the code looks like, or maybe that's too long to show?
Oh, I didn't put it, but I have here.
Just
so
put the
in the
browser
end,
there.
I can.
You should
I
go
can
ahead.
show a explicit case of the algorithm. Okay, even the script, Python script, and also in C, I can show in the end.
So if I have a data set, can I write everything in Python, for example?
Yeah,
So
I
I
think
can
currently
all
you
the-
can
There
define
is
all
just a
objects.
one sad thing is that the C Python currently has a global thread locker. So you can do everything in Python, but if you try to parallelize it, you're going to have a huge problem. Because every time you call Python, it blocks everything, all threads.
Okay.
But yeah,
That's a Python problem.
yeah, it's a Python problem. Yeah. But if you're doing it in Perl, you don't have a
So,
problem.
Marianne, you should probably hurry a little bit because we're going pretty slow.
Yeah.
Okay.
There's-
Okay, so following this idea, we have, for example, the primordial spectrum, transfer function, and growth functions, and so here is the structure for the for cluster number counts, for example. This is just the model part, okay? So differently from the simple case of supernova, here we have our model set composed by the primordial spectrum, the dark energy cosmological model, or the cosmological model, cluster mass, and cluster redshift, okay? And all these are inputs of this object NC cluster abundance. But NC cluster abundance receives what? Mass function, which we saw that depends on the distance, matter variance, growth function, and multiplicity function. Matter var on the other side depends on the transfer function and with window function and so on. So, but for the model, which are those objects which I want to define parameters to be able to fit them, I will define like this, like a always a child of NCM model. And for example, another thing that we discussed in Euclid is be able to fit, for example, a multiplicity function. So in this case, we can easily transform this guy here as a child of NCM model, okay? So these modifications are also simple.
So how do you distinguish, what's your criteria for breaking up between the two colors? So the NC multiplicity function here is under the cosmology library, but other stuff is up there under the model parameters, under the NCM model. So what's the criteria for?
The color series I use just to differentiate who is a model,
And
which defines a set of parameters and other objects. But for example, I can put, for example, mass function as another color, and then in green, and then those ones as a yellow.
But then my question is why? So it's related to the
With
question,
the
the
arguments.
point you just made. Why is the multiplicity function here under NC and not under NCM model?
Okay.
What's that? Because go ahead.
Here NC is under NC because it's just related with the cosmological feature quantity, and nowadays currently it's not a model. I cannot fit.
Oh, I see. Okay.
I cannot fit any parameter of the multiplicity function here today. But if it's necessary, we can transform it in an NCM model. We can do this. And
It's just a
then,
matter
in
of
this
changing
case,
its parameters.
multiplicity function,
Okay.
it will be here
So,
along with the other models.
right. So, for example, if I wanted to fit a modified gravity model, then the piece that calculates the growth factor that goes into the multiplicity function is actually going to end up under the NCM model. Because I'm going to want to fit a parameter for the modified gravity.
Okay, in this case, for example, if we have a FR gravity modified gravity model, and we have a multiplicity function which were obtained from a suitable n-bar simulation using this FR model, you can have a new class. Here it will be a general growth function, for example, which will have now simple gravitational growth function, and it will be a new branch for this modified gravity function.
Right.
So this guy here will be an abstract class, and we will have now 2 children for modified gravity and growth function given general relativity.
Right.
Because nowadays we
Including-
have just for general relativity. This is why it's simple. But in the future we can do this, and then this will be an abstract class with 2 children. FR growth function for FR cosmology and growth function for GR, for example. And then multiplicity function, it will probably continue like this, but you have to assert that if you want to use a multiplicity function which is defined just for general relativity, you have to make sure that you are using all the other components appropriately, you assuming GR. But it will be under the same object. You can break. Okay.
I think as long as the growth function is just a simple function of d of z, you can always create this abstract growth function, and then you have different implementations. In our case, we have just the current GR implementation.
GR, yeah.
We haven't the need to create a structure there. But it's like that. The growth is like that.
You've got about 10 minutes left.
Oh, sorry. And if I have, say, some deviations in spectrum of density fluctuations which arises as cosmological consequences of particle theory, so that, for example, you don't have lambda CDM, but you have something warmer than CDM.
Mm-hmm.
How can I arrange my contribution to your analysis? In which terms, because I know physics, but just in which mathematical terms should such modification come? Because another possibility is that you have some effect of decaying dark matter particles, which also change the equation of state and also mass of the growing bodies changes. So how these
how does somebody
modifications-
who doesn't really know much programming change something in here? Put a new model in, I guess is the question.
This is the nice thing. If you have a specific model for another cosmological model, you will implement a new object. So if in your model your background is homogeneous and isotropic, okay, you have already this object, and then your part your part it will be a sum of this one. Okay, so you have all the features that already exist for this guy, and now you can create your specific model. Like here we have dark energy XCDM. You can create this warm dark matter model, and it will be a child here.
So about how much code would it be to do something like this? If I have
in the simplest case, for example, you just need to provide the Hubble function square.
Okay, so you
simplest
just
case.
square
You
root
just
of
want
omega.
to change a little bit the background evolution. But if you want to change perturbations, so now I'm working the code to make this same kind of plug-in interface also for new perturbations, degrees of freedom. So we have also the basic Boltzmann equation, but now you want some
So if we want to put
scalar field
tensor
perturbations or
or
tensor
vectors.
or coupling between them or something, then I'm working on this interface right now. But at this point, you can change the background, you can change the growth function, you can change the transfer function. But this new perturbations is still a work in progress.
And I'm sorry, but I need to hurry you.
Okay, and in terms of algorithm, for example, if you implement in C, your object, it will be a .c file and a header.
You can give the example of the different power spectrum, primordial power spectrum. It's very simple to see different implementation.
Okay. Mm-hmm. Okay. Oh, and this, but we have all this structure. But for example, cluster mask depends on the cosmological models. NC distance, we saw that it depends, and many other functions. But the structure of the NumCosmo deals with it. For example, and when I'm going to fit, I'm fitting some cosmological models, some cosmological parameters. So one step of the minimization or the MCMC algorithm, it will compute for a given set of parameters, it will compute the value of your likelihood function, and then it will change. This modification of the cosmological parameters, it will happen here. So in this model, in this object, but it will. There are many other objects here which depends on the high cosmos. So we have here a control of each object which depends on this, such that I can assure that at each step, all functions, all properties here, all objects are being modified and calculated properly, giving the same set of parameters. Okay, so we have this control.
So, for example, if you just change the value of H naught in the Cosmo, it's propagating only for those objects that depend on H naught.
That's but those very useful. It's really useful.
Yeah.
I'm really worried you're not going to finish in time.
Yeah. Okay. Yeah. So this is an example of a combined probe. So here, if I want to combine supernova and cluster number counts, our model set will be composed by those for cluster number counts, and here with the supernova covariance distance. Okay. And here we see that my observable NC cluster abundance, in this case, it's not a model, but it can be, as in the case of a supernova. So because here I have some cosmological, I have some experimental parameters that I want to fit. So it's useful to define it directly as an NCM model. In our case, our pseudo counts, cluster pseudo counts, are also in the same model because we are modeling the selection function inside it, and we are fitting those parameters. So in our Planck clash work, okay. So to fit the NCM likelihoods now, I want to fit the inputs data set, which now will be composed by data cluster in count and also the supernova in count, okay. This one I want to point out here first. Quality assurance, because this was also discussed in Euclid meeting, that for example, if they performed a challenge comparing many algorithms that were developed by different members, okay? And they checked that some of these algorithms were varying and were introducing error more than 1%, giving just the definition of the fundamental constants. How many, if you are using just three numbers to define, or algorithms to define, okay? So here in NumCosmo, we use CoData, IAU, and NIST, and other.
So if you put pi 3.14, for example, you get a wrong.
Yeah, I was surprised with it.
Well, if pi is wrong, you will get the wrong answer, I'm sure.
But it depends on how wrong. 3.14 is 1 per thousand.
Okay.
But it's hard to know how this error propagates. sometimes.
I agree. It's surprising.
No, and yeah, for me it's also a surprise when I saw this last week, and this is why I point out this in NumCosmo, okay?
It's also surprising that people just don't put the entire chain of 20 digits.
Yeah, it don't matter.
Yeah, exactly.
Sometimes it's useless. So sometimes depending on your process.
It's for sure useless, but at least it's not, you can never
It
get
will
it
not
wrong.
be a source of, yeah.
But Martin, you really have to hurry now.
Okay. And for example, we also should implement a test file for each object. So this test file will guarantee that when you install NumCosmo in your computer, you can make check and see that each object is behaving properly, okay? Because each one will be a test, which will have a test file. Group function is another example. There are many algorithms that people using the literature, which just solves an integral for the growth function. And here we solve the differential equation. These are just examples. Another thing that was discussed last week, how to define the Tinker multiplicity function for critical mass density. Using linear spline or not, or if my delta is not defined given as for fixed parameters from Tinker et al. Paper, how can we do this? And people discussed, there are some guys that are using linear interpolation, and here our implementation use cubic splines, and we define everything. For example, we have some functions for the interpolation algorithms, which you can define the knots of your spline given a precision. You choose a precision, what precision do you want, and then the knots will be defined such that you satisfy your interpolation will satisfy this precision, and then everything is controlled this way. Okay. SimB stats, Sandra is working on this. Class and the Planck's likelihood are integrated in the library build system. The abstract Planck foreground and instrument models are defined by these two objects, okay? And for now we have the TT version. Class interface is described in this backend object. Interface through CL, through these homogeneous isotropic perturbations Boltzmann, and Planck's likelihood is defined in this data object. Okay. Currently, we have a working version of this Boltzmann code, and based on the backend, class backend. Okay. The NumCosmo will have an implementation that Sandra is working on this. And for example, models with invariant, gauge invariant, okay, for
This implementation will be gauge invariant from the beginning. The whole numeric is going to be on gauge invariant variables.
Can you link with CAM or not?
Well, yeah, but it's the license that they use is not so free, so I cannot distribute it together. So I could not build this integrated building system, because right now you just compile my library and you are compiling class and the Planck likelihood together.
Yeah.
But CAM I cannot distribute with my library, so I cannot do that.
It's probably easier to program class.
Yeah.
I would think.
Yeah.
Alternative primordial power spectrum, for example, interface, and here we have read another example besides the power law, simple power law, okay. Thermodynamics through class, we have this recommendation class backend, and also an independent implementation, which Sandro did based on seizure paper, okay. And interface to class meta transfer function will be integrated in the next release. And here we have both growth function, the spectrum growth function and transfer function will be given. This will be a function of k and also redshift, okay? These are the observational probes that we already have implemented in our library. This cross correlation aspect here has been developed by Cyril in his PhD. Yeah. And these are the data analysis tools. So, for example, for Best Finder, which I mentioned that we have more than 70 algorithms, different algorithms, because we have this link to these different libraries. Okay.
You forgot to add the nonlinear optimization library.
Yeah, NLLPT. Yeah. So if you want to compute Fisher matrix, this function is defined inside the NCM fit object. If you want to perform a Monte Carlo analysis, you have already this implementation. Monte Carlo from Bootstrap. If you want to perform a frequency analysis, we have the algorithms to compute the profile likelihood in one dimension for one parameter, or to compute the confidence regions in a bidimensional space. Okay, you can have you can marginalize over other parameters. Okay, and Bayesian analysis, we have the Metropolis Hastings algorithm. This is not multi-threaded, but we have the ESMCMC, which is multi-threaded and much better than the simple one. Okay, and we also have an implementation of approximate Bayesian computation. In this case, it's a methodology when you have a problem where you don't have defined the likelihood, so you can use this kind of algorithm. Okay. Here is an example of some scripts that we provided together with the library with NumCosmo. So we have, for example, this script, MCAT analyze, where you can compute the 1, 2, 3 sigma confidence intervals from the best fit for the mean, from the mode, and so on, and also compute the covariance matrix together. If you perform ESMCMC, where you fit both cosmological and experimental parameters, this covariance matrix will be the huge one, taking into account all these parameters. And we also have distributed these scripts in Python, for example, where you can perform. You can get plots like this, where you have the histograms of your posterior, of your likelihood, okay, in bidimensional space, and the 1, 2, and 3 sigma contours, and also this corner plot, okay. We provide these 3 scripts together.
Just to add to that, our tools always create a catalog that's a fits file. And all this same fits file can be analyzed by the MCAT analyzer. It's just
or you could put your own.
Yeah, of course.
Yeah, and that's it. So we think NumCosmo is a suitable framework for collaborations and for collaborative work. And as we mentioned, you can implement your object directly in Python, for example. Okay. Here are some references where we use and describe a little bit some of these objects that we define in the library. Okay. And the NumCosmo paper and the paper for the NC XCore module, we are working on this, okay? So I think it's, and that's it.
Maybe you can show that in the
you
browser.
were gonna show examples of, like, I don't know, if I wanted to put a lens in something, how do I do it? Is it just
So
long?
when you put it up, just a question, have you compared CAM with your implementation of your solution of Boltzmann's equation?
Yeah.
And for example, for the transfer function, what
I
level
have
do you
the same result, up to 10 to the minus 4.
Wait, so,
At least
so
now.
you wrote the Boltzmann solver, or you're
I have
you've
one
integrated?
Boltzmann solver, but I did it in gauging variant, and I have to. There is some problems in the equation, so it's a numerical round-off here that we have to
Because
solve. So
wasn't there on Planck, there were some comparisons of two Boltzmann solvers?
Well, there's, I think it's written up, so I think Julian Lescourt wrote some paper solving, comparing
the
class.
tight coupling approximation.
And he did some studies comparing class and count.
For example, I just fit Planck likelihood using a model that I'm working on, and I got the same parameters and fed to Cosmo C, and I got the same result. So I have the same value for the likelihood given a set of parameters in both my code and Cosmo C.
What about processing time? How does it compare to time?
Well, it's about the same, I think, class and chem, but that depends on the precision parameters, and that's very complicated thing because you go about 100 in class and some weird parameters in chem. So it's hard just to know what's exactly the precision of the theoretical calculations.
One comment, I had some bad experiences doing simulations in the gauge invariant or Newtonian gauge because
it's very hard.
The nice thing about the synchronous gauge is that the perturbations are very small on superhorizon scale, so you've chosen a gauge where they're small.
Yeah.
And I don't know, it's something to be
No,
very
that's
careful
true.
about.
But what I'm doing in this case is that if you take the gauge invariant variables, usually use it like the phi, capital psi, they are the same as the Newtonian variables when you go to gauge invariant variables. But you can choose different combinations of gauge invariant variables that resemble like synchronous gauge variables when you go to these gauge invariant variables. So we can try to, because this is some way to prevent the numerical problems. But I'm also trying to do something a little bit better, but it's not really yet. It's just because the problem is that you have a lot of first order variables and second order variables. And when you write everything as first order variables, you just have a lot of contributions to your code that comes from difference of very similar numbers, and that's the very big nasty problem in numerics. You have difference between the difference between the velocity of baryons and velocity of radiation that goes almost to zero initially, and you have the tight coupling problem, and this happens everywhere in your code. Because in a sense, initially you have only the adiabatic mode. The other modes are not there yet when you start the integration. And so everything is just one degree of freedom. The other degrees of freedom is just being excited at that point. So that has a consequence numerically.
Okay, do you want to just show?
Yeah.
Just drag the browser. Oh, okay.
This is an example of an implementation directly in Python. So this is a an alternative primordial power spectrum. Okay, so here it's how we call the NumCosmo library. Okay, and we are going to import all the NC NumCosmo and NumCosmo math objects. Okay. So here, let me see.
So just create a precision object for the class backend, and then you increase a little bit the number of K per decade because you're doing some weird stuff in the background, in the power spectrum.
So this is all of the code. None of these things are code that you had to write. And none of the calls are all stuff that's in NumCosmo. It's not stuff that I have to write.
Yeah.
You don't need to do anything. Yeah, you
don't
just
need
need this script there.
You can play and define a new primordial power spectrum. You can copy this example and implement parameter.
So now we create the Boltzmann object from this precision Boltzmann object. Yeah. And then you set the maximum L that you want to compute and the target that you want, just TT, and then if you want lens and power spectrum, and please go on. Now you define what the background cosmological model. They set one of the parameters to 0 just to make it
You
simpler.
are defining a flat universe given a W constant dark energy, for
Yeah.
example.
And here you are changing the variables from omega x to omega k. Just
A reparametrization.
so then here you prepare your results using that primordial model and the cosmology model that you choose, and you create vectors to get the results. So here I'm just putting one of the parameters to 0, so it will resemble the standard power spectrum. And then I calculate, so I have prepared here, and then I change one parameter and I prepare again. So I have the two results, the CLs with that parameter different from 0, and the CLs with the parameter equal to 0. But it should be better to show through the web browser, because there...
I don't have internet. I don't have
Okay.
connection.
Well, why don't I suggest? I mean, we know where you live or where you work, and we'll come and find you and ask you about it. Yeah, I think we're not going to learn everything right here. So, are there other questions or things? I mean, I was hoping
I
that.
just have just one kind of practical question. So presumably you could do a PhD using your code without learning any C.
Yeah, the guy in front of you is.
Okay.
Yeah.
No,
Without
no,
learning? No, but he's
Yes,
implementing. He's a
but I'm
developer.
thinking of job prospects for anyone who uses your code,
Yeah.
because that's a very practical problem today.
Yeah.
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 So the industry standard seems to be Python or C++,
Yeah.
but not C. C is very rarely used outside.
Yeah. The problem is usually you can start in Python and you have something going, but at some point you probably want to migrate some pieces of it to C.
Okay.
But in that direction, I think it's much easier for most people. You have some results very slowly, but you do everything in Python, and then you choose that part that's slowing down your code to go to C. That way, I think it's very flexible.
Okay, we do have to. So yeah, you're the last person.
Yeah, so if you have Python, then you said that there's a problem in doing running things in parallel chains, right?
Yeah,
Bootstrap.
threaded.
So it cannot be done in Python.
You can
if you
do
want
it.
to run parallel.
Yeah.
Okay. And what is this advantage apart from this galaxy cluster number count, which is maybe a new thing? Advantage in terms of if you compare it with Cosmo MC, for example.
Well,
I mean, it is also object oriented, right? Yeah, it uses Fortran 2008. I mean, at least the last 2-3 years, person is using. It has a separate object for likelihood, separate object for different theories and all that.
The main difference is the breakdown that we discussed. How our libraries break down to the last bit, so you can just tweak here and change there. If you want to change something in Cosmo C, you want to have to deal with a lot of things at once.
No, I'm saying for the recent version of Cosmo MC, which uses Fortran 2008 or object-oriented things, then if you want to add a likelihood, it's very simple, I guess. Just add a file which you say that this is
Just
this
one
object is
file.
of the type of likelihood, and it takes the nuisance parameters and things like that.
Yeah.
So
So to use it, it will be about the same, but to implement new things
it will be easier.
Yeah.
Okay.
Okay.
Another
no,
question, how can I contact you to propose my non-trivial scenarios?
She's in the office She's in the office with Eric and Julian, just over there in B.
438B.
Okay, but I have to stop it now.
I can send you our email
Yeah.
and.
Yeah.
I'll send you each an email. Let's thank her again.